In this video, we're going to take a look at Gay-Lussac's law. Now, Gay-Lussac's law is a lot like Charles' law in that it has a direct relationship between temperature and, in this case, pressure, but in Charles' law case, it is volume. So Gay-Lussac's law says that pressure and temperature are directly proportional. That means that if the temperature is increasing, so is the pressure. Now, this depends on the gas having a constant volume and chemical amount. So usually we'd think about that being like a container that can't expand or contract. So maybe like a propane tank or something like that that's rigid and it's got a set amount of gas in it and then it's either being heated or cooled. So the formula is P1 over T1 equals P2 over T2. So when we do a question like this, one of the key components to it is making sure that we identify what our pressure and temperature are. So here I've got a question that says, what pressure does a gas sample at 95.0 kPa and 20 degrees Celsius end up with if it is cooled to minus 50? So we've got a P1 is 95.0 kPa. And importantly, this is the temperature that's happening at. So even if you didn't know if it was initial or final, as long as we get the pressure and the temperature connected, it'll work out. So you have 20.0 degrees Celsius. But for all gas law questions, this needs to be converted to Kelvin. So it's 293 Kelvin. P2 is what we're trying to find out. And T2 is, it says negative 50 degrees Celsius. So this is going to be 223 Kelvin. So my P1 over T1 equals P2 over T2. If I want to solve for P2, I need to get it by itself. So I'm going to get P1 T2 over T1. And so the way I kind of explain this is that this, if I'm going to get rid of this, as it crosses the equal sign, it's going to go into the numerator. The reason that it does that, though, is because I'm multiplying both sides by T2, and these two T2s cancel out, and I'm left with P2 being equal to T2 P1 over T1. So that's my rearrangement. And so I get my P1 is 95.0 kPa times T2, which is 223 Kelvin, divided by 293 Kelvin. That's my T1. And this is going to give me 72.3 kPa. Now I've got 3 sig digs for all my numbers here. I want to like a little bit of a double check. My pressure has gone down, but it's also cooled. So if I have my temperature is going down, my pressure is also going to go down. So that kind of makes sense, and so it's satisfactory to me. The next question I'll do is asking about temperature. So here, what temperature is a tank of propane gas if it is at 101 kPa at 25 degrees Celsius? So those two amounts are connected. We'll call them 1. So this is 298 Kelvin, because I always do my gas calculations in Kelvin. If it asks for degrees Celsius as a final answer, I then go back from Kelvin to degrees Celsius. My P2 is 220 kPa, and I want my T2. So P1 over T1 equals P2 over T2. My formula is going to be T2 equals P1 over T1 times, oh, no, hold on, I'm getting that one wrong. Let me do this again. I'm going to get P2 over P1 times T1. Now, this is the harder rearrangement. Because I want T2, I need to get it out of the denominator. So I put it up here, and so what I get is P1 T2 over T1 equals P2. But then I want the T2 by itself, right? So I'm going to take my P1 to the other side, and it goes in the denominator. My T1 goes up here to leave me with this formula. So I'm going to substitute in. My P2 is 220 kPa. I can see I copied that down wrong here. And my T1 is 298 Kelvin. And my P1 is 101 kPa. Now my units agree here. If they weren't the same kinds of pressure, then I'd need to convert one of them. It doesn't matter which one, they just have to cancel out, right? Here, so I've got kPas and kPas. So I'm gonna put that into my calculator, 220 times 298 divided by 101. And this gives me a T2 of 649 Kelvin. Sounds huge, and that's hot, but it makes sense. If my pressure has more than doubled, my temperature must have also basically doubled. And so if I wanted this in degrees Celsius, this will be 376 degrees Celsius, because to go from Kelvin to degrees Celsius, I subtract 273. Hopefully this helps you out.